Hi everyone. In this video I have explained the improved Euler's methods, and this method basically will be used to compute the approximate solution of the differential equation y prime is equals to f of xy numerically. So basically in the last class we learned about the Euler's method. Now in this class, in this video I am basically explaining improved Euler's method. So what is the improvement? So we were looking for a better method than the Euler method, because as we know that in the Euler method error is um, error is of order 1, where h is a step size. So this is for Euler's method. Now, can we, from the previous method, can we improve the error in the sense that can we get a lesser error of, or one can say, can we get an error of higher order than the first order? Like higher order in the sense that say c constant time, this c is a constant here, constant time h square or constant time h cube. So if it is constant time h square, it will be of second order accuracy, because so it is not in the context of the order of a differential equation, because in um, in this first few sessions we are only understanding how to solve first order differential equations. So differential equation will be of first order, but Euler's method, uh, when we compute the approximate solution using Euler's method, the error turns out to be from the exact solution of order h. So this is the idea behind the Euler's method. This was the idea, but now second question comes up in the mind: what can we do in order to improve our numerical method? So therefore we come to the improved Euler's method. Now what does this method tells us? So first of all, just recalling the concept of finding the approximate solution, basically we can see here that x is the domain given to us in which we are trying to find our solution y of this differential equation. So suppose x is taking the value x0, x1, x2, and so on. We pick up few points on x-axis and we want to find the approximate solution at these points. So and the difference between x0 and x1 is h. So with the step size of say h, so we have a step size here, h step size we are moving, and we are looking for at x0 what is the value y0, at x1 what is y1, x2 what is y2, and so on. Now you would be, first of all let's get clear with the notations here. So what does we mean by x0, x1, x2 and x3? So x1 step size h. So h here is a step size. x3 will be x2 plus h, and so on. You go till the uh, end of the interval in which you are trying to find the solution. Okay, so suppose you are looking for a solution in the interval x0 to xn. So this is your starting point. We are talking about only the forward Euler method because we are moving in the forward direction. X naught plus h, x1 plus h, and so on. We take a small step size and we go till the end point. So in this interval, suppose we are trying to look for a solution. So the termination will be at xn equals to this. Now corresponding to each x1, I have named them. I'm basically looking for. So here I should write looking for. I'm looking for y0, y1, y2, y3. So now what does these notation mean? So y0 is nothing but the initial condition, y at x0, and y1, this is exactly equal to, and y1 is basically approximation to the exact solution at x1. y2 will be approximation at point x2 of the solution. y3 will be an approximate value at x3. So these are approximate values. So these are the approximate values of the solution. Okay, so we get the approximation the moment we have approximation. Suppose y0 is here, y1 is here, and another point here. We use another kind of interpolating technique which you will learn later on, and you kind of fit a curve uh, in all those passing through those points. And if your step size is small, your curve would might be little more accurate. So this is a rough idea, but there's a lot of depth still inside or through from the analytical point of view. But first of all, I would give you the overview how to solve a differential equation using improved Euler's method, and then we will learn about the gaps in it, or uh, what exactly we missed. Are we getting really a nice solution? Can we get a better solution? So these kind of questions we'll address later on, but first we'll focus on how to solve numerically using this method. So h is decided and will be given to you. Is a step size. Now uh, how would we go about thinking the solution of this problem? Now in Euler's method, you have seen it's just a definition of a derivative which we used the first definition, the limit definition, to find the derivative, and we got the approximation of a solution. So what we will do, is there any other way we can think of uh, designing a scheme for a solution? So very one naive thinking could be, let us integrate both the side. So even though we don't have f, let's integrate and see how much we can simplify, how much we can use our previous knowledge of calculus and get an expression. So after integrating both the side, we will get what? So and let's integrate in the very small interval with first uh, increment, that is x0 to x0 plus h. Just in very this tiny little interval, let's integrate this function. Okay, so x0 to x0 plus h y prime dx is equals to integral x0 to x0 plus h f of x comma yx dx. Now what can I do here? Here I can apply fundamental theorem of calculus, right? Using fundamental theorem of calculus, what we get, y at x0 plus h minus y at x0 is nothing but, now what can I do here? What can I do in the right hand side? Well, do I know any formula of integrating a function when I don't know the function? When I only know the function value at certain points? Is there an approximation to an integral? Is there a formula? Yes, we do have, and that is trapezoidal rule. So we will use trapezoidal rule to integrate the right hand side. So f of x naught y at x naught plus, and this is approximation, f of x naught plus h comma y of x naught plus h. Okay, so this is using, this one is using trapezoidal rule. Okay, so far so good. So we have this kind of expression. Now this term, okay, let me use another color. This term is what? In our previous notation, this term is named as y1, right? Y at x1. This is x1. X naught plus h is x1. And this is as y naught. So now we are looking, we are coming towards the next approximation y1, using the first approximation, which is initial condition. So using initial condition, we are finding the next approximation. So y1 minus y naught, and this is approximation. Now I will keep it equal, but you already know that we are basically approximating we are finding the approximations through the numerical scheme, this numerical scheme. Now this is nothing but, I can write here f of x naught comma y naught. Going back to my previous notation, this is y naught plus f of this is x1 comma y1, right? So this is what we have. Okay, so now I can simplify this expression furthermore. I'll add y naught both the side, and I will get this expression. Okay, now there is a thing here. So one thing is clear, that we are finding basically y1, and we are only given y naught. And we are finding y1. So in this expression, I can see that y1 is appearing here and as well as here, right? So y1 is appearing both the side. So how can I get the value of y1 if y1 is in both the side? I can't simplify for y1 here. So because of this reason, y1 above expression is implicit expression of y1. So what should we do then? Well, we should now try to think, can we use some intermediate value between y0 and y1, which we can put it here, so that we can get y1 a better approximation, right? Because in Euler's method, what we did, From the y0 we approach towards the y1. But in this method, we kind of using at 2 points value of slope. So basically we are using two slope to get the y1 approximation. And two slopes is kind of averaging the two slopes here. If we compare this with Euler's method, this is like averaging two slopes. So geometrically, this is getting much closer to the curve by averaging the two slopes. So so like for example, if you have the function like a solution, exact solution like this, then at this point you started, say x0 y0, and you had little tiny line segment, tangent, slope. So this is kind of cheating. It's very seems to be very close to it. So something like touching this. So this tangent we had. Then we got here y1, and we found another tangent. So basically we had this slope y0, we had this y1, and now when we take average of it, we will go little bit nearer to the curve and further from these two um, schemes. So for example, if it's Euler, it would be moving like something like this, then this, then this, uh, but it should be very far from the exact solution. This is exact solution, and this is approximate solution. But improved Euler will be going little closer to it because it's averaging here. So okay, this is the background idea. So I need to find intermediate value which is between y0 and y1, and which I can plug it here. Now there should be a certain uh, systematic way of finding it. It's not like just picking up the any value and getting the thing. So I will write that intermediate value. I will name that intermediate value as z1. So that is the intermediate value, f of x1 z1. Okay, so now what is this z1? How will I pick this z1? Do I know any way to pick this z1 systematically? Yes, I do know. I will make use of Euler's method here. We will pick the intermediate values approximations using Euler's method. So we will use the Euler's method and we'll find the intermediate approximation. Then we'll take average of two slopes, get more closer to the curve, and find our y1. So therefore y1 turns out to be y at x y at x0 plus h over 2 f of x0 y0 plus f of x1 y0 plus h times f of x0 y0. So this is how y1 will come after plugging the z1 value using this. So now you can see this y1 is now free from y1 in the right hand side. So we can get the value of y1. So like this we keep on finding the values. So let's write the steps the improved Euler method. So improved Euler method, scheme. H step size is given to you. Then second point is we have to figure out what is the initial condition. It will be also given. Sometimes it is given, and when you go further, like when you learn different courses and go towards a problem which it's like a research problems, then maybe some, and most of the time you need to think what you have to pick your initial condition. But at this level you would be given the initial condition. Now the second point is find z1. Using Euler's method and using initial condition, find the intermediate approximation. Getting the intermediate approximation, go for first approximation of a solution, which is y naught plus h over 2 f of x naught y naught plus f of x1 z1. Now for this, I assume that you would have understood that when h is given, definitely you need to find these points x0, x1, x2 till xn, and which is nothing but x0 is initial condition, this is x0 plus h, this is x0 plus 2h. We are moving with the step size uh, of h. Getting y1, uh, so getting y1, then further keep on finding like this other approximation. So in general, zi will be nothing but yi minus 1 plus h times f of xi minus 1 yi minus 1, right? Yi will be yi minus 1, the approximation, the ith approximation in terms of I minus 1 approximation, f of xi minus 1 yi minus 1 plus f of xi zi. So, well, so approximations to the solution yi, okay, so this is the approach. This is the approach, and that's right. Like yi means y at xi, and similarly everywhere xi is x naught plus ih. So well, so these are notations. What is yi means, what is xi means, and zi similarly is intermediate approximation, which is z at xi. Okay, so let's now solve a problem. So we have a problem here, example listed, and we'll solve this example by hand, and then we will use the Excel also to solve this example. Okay, so what we have to do in this problem, the reason I picked up this problem, so mainly you would be learning, you would be using the numerical method for the problems you can't solve. So you have, say suppose you have y prime equals to sine xy. Now this is impossible to solve by hand, this differential equation, but we can find the numerical solutions of it. So we will apply these kind of methods to this type of problems. But the reason I picked up the simplest, very simple problem which we can even solve by hand is to compare my exact solution which I get from my approximate solution. That was the reason to pick up this example. Okay, so coming to this, give the solution give the solution to the initial value problem IVP y prime equals to 2x plus y initially at x equals to 1 is taking the value 2. Then create the approximation using improved Euler's method with a step size of h equals to 0.1 and compare the results to the true solution on the interval 1, 2. Okay, so this is the interval over which we are finding the approximate solution. So first of all, just we will form a, basically you have to form a table, and then, so let me draw a little table here and then keep filling the values in that table. So one column will be of xi, another will be for say f of slopes, then another one I can put for zi and yi. Okay, and hi fix here 0.1. So x naught is 1, x1 is 1 plus 0.1, which is nothing but 1.1, right? Which is 1.1. x2 is 1.2, x3 is 1.3, and we will go till x10, which is 2. So 10 steps. Now f of xi yi. What is f of xi yi? So f of x naught y naught is nothing but, let me move this line little bit further, 2x plus y, right? 2x naught plus y naught. So what will I get from here? 2 times x naught is 1, y naught is 2, so 2 plus 2, 4. Then similarly we find x1 y1. Maybe we need x1 z1 first, and those kind of values. So we will fill in those also. Now what is yi? So first zi and then yi. So z1 is nothing but y naught plus h times f of x naught y naught. So y naught is 2, h1 is 0.1, and f of x naught y naught is 4. y1 is y naught plus h over 2, that is 0.1 over 2, f of x naught y naught plus f of x1 z1. So like this we need to fill in the table. So let's compute the z1 is here 2.4, and what is y1? So let's find the values here and then pick and plug them back in the table. So z1 we got 2.4. Now y1 is 2 plus 0.1 over 2, f of x naught y naught 4, f of x1 z1 is 2 times x1 plus z1, which is nothing but 2 times x1 is 2.2 and z1 is 2.4. So 2.2 plus 2.4, and this is 2 is division is outside. I have divided already 4, and I will divide this by 2 also. So simplifying this, I should get here, let's see what will I get. So 4.6, and 4.6 divided by 2 is 2.3. 2.3 plus zero point 0.2, so here 2.3, 2.3 plus zero point 0.2 is 2.5, and 2 plus 2.5. Yeah, so is it correct? Let's check once again. So we had 2.4 here. Y naught is 2.1 over 2. Then, yeah, I didn't multiply 0.1 in this expression, right? 2 times x1 is 2.2 and z1 is 2.4, but 0.1 I multiplied in 4 and divided by 2, but 0.1 I didn't multiply it here. So multiply 0.1 here. So if you multiply 0.1 here, you will get here so what will we get further? 2 plus here 0.2, and then it is 4.6. 4.6 is 0.46 divided by 2. So we have here 2 plus, seems little, I think it's okay. So zero point 0.2, we'll check with Excel. A calculation we can check. So it's 0.23 and it should turn out to be 2.43. So that will be our y1. Having the y1, going back to z2 now. So z2 is nothing but y1 plus h times f of x1 y1. So y1 is 2.43, h1 is 0.1, and f of x1 is 1.1. So 2 times 1.1 plus y1 is 2.43. So this gives 2.43 plus 2.2 plus 2.43 multiplied with 0.1. So we have here, so we have 4.63, which is 0.463, and therefore we have 2.893. So this is Z2. Having Z2, let's write the value here. Z2 is 2.893. Z2 is here, so Y2 we have to find now using the Z2. So Y2 is Y1 plus y1 plus h over 2 again, 0.1 over 2, f of x1 y1 plus f of x1 z1. So now what is z1? Z1 is 2.43. So just plugging it back, z1 is 2.4. Yeah. But for y2, we need to plug in x1 y1 is correct here, but here I should use the z2, right? I should use z2 intermediate value, so x2 z2 to get this. So 0.1 over 2 f of x1 z1 is what? We already computed it here, 2.2 plus 2.43, so therefore it turns out to be 4.63 plus f of x2 z2 is 2 times x2 was 1.2 plus z2 is 2.893 and bracket close. Okay, so let's simplify this. So this is, we get here 2.43 plus, so simplifying this expression, 4.63 we have, then we have here 2.4, then we have here 2.893, so it should be 10,91489, 9.923. Now divide by 2 and multiply by 0.3, so you get here so you should get here 2.43 plus 0.49615. So if you add this thing up, so 2189, 2.92 615. So this is your y2, and similarly you keep doing and get the y10. Now in the exam I will be asking you only couple of steps, but in the problem set you have to do lots of steps. So for that it will be a good idea to use Excel and find it. So let's go to Excel.